Thank you guys for joining once again. So how many of you have attended my previous sessions? Anyone? Okay. So as I've already mentioned, probably it was clearly mentioned in the description. This is more or less going to be in continuation with what we have been doing. Let me quickly share my screen. So the previous session was on artificial neural networks, basic vanilla neural networks, you can say. And I'm expecting the participants to be familiar with the basics of neural networks. Can I assume, or shall I have to start from scratch once again? Yeah. Can I assume? I'll be able to cover more topics if I directly can assume. Maybe I'll have a quick revision. No worries on that. Okay. But the previous session video has also been uploaded on YouTube in our Analytics Vidhya channel. Okay. So if you want, maybe I can share that link. So for the learners who are completely new to these neural networks, I think that will really help. There is no sound. Is that Kumar? I am audible, right?
Yeah, it's crystal clear.
Okay, thank you. So maybe people who are facing some challenges, you can definitely rejoin the session. That works many times. Give me a minute. I'll be able to share my screen. I'm just getting things here. Okay, I'm trying to find out that link for the previous session so that learners who have missed be able to catch up from there. And as usual, I do not have a lot of PPTs. Mostly we'll be discussing hands. That is a better way. And then at the end of the day, I'll share the link for my GitHub where I have posted all these codes. So you would be able to download it, right? But only at the end of the session, not during the session. So during the session, I want everyone to pay attention to what I'm discussing. The screen share is visible to everyone. I'm sharing this link with the learners, participants here. So this was the first session on the series of sessions that I would be delivering on neural networks. So this is the second part. Today's session is the second part in that series. So this was the link. This YouTube video was, this was the first data session on neural networks, and this was taken on, I think, 27th of March. I don't remember the exact date, but that was around that time. Okay. So anyone who is completely new to neural networks is strongly suggested to please go through this. This was more or less almost a 2-hour session. You can see it's again a 2-hour session, and most of my sessions have been like 2.5 hours. Okay. Although this is called as data hour, but it runs to claim data couple of hours and even more maybe. So today I'll still try to wind up within the stipulated time plus minus 15-20 minutes. Okay. It won't be minus more or less. Okay. So this is the prerequisite which I had expected. And if you are coming with that background, fantastic. We'll be able to enjoy. If not, please go through this and still you will be able to get something, because I'll quickly revise in maybe 10-15 minutes why we need or what is neural network, why we need neural networks, and how are different architectures of neural networks, and then why CNN and so on, right? So let's get started. So I have a couple of slides, not more. So I'll not go back to discussing what is deep learning, what are the advantages of neural networks over machine learning. So all those things we have already discussed. Okay. Application areas and everything. Okay. What is a neuron and so on. But probably one thing that I would like to start today is from here. Okay. Just to set the context and flow, more importantly. Okay. So basically, this is a single layer network. It's a single layer network. Okay. The first layer that you see is the input layer where you feed the features. Okay, everyone is aware of supervised machine learning. So today, this is supervised deep learning once again. But this time, the special type of data that we'll be discussing is images. Okay, but this is more or less still supervised. So this output neuron will give me the predictions, which can be numbers. In that case, we are solving a regression problem, or it can be a categorical label. Okay, so like male, female, cat, dog, Prashant, no Prashant, something like that. Okay, so if the output is categorical, then we are solving a classification problem using a neural network. And if the output is a continuous number, let's say from minus infinity to plus infinity or 0 to plus infinity, any continuous number, it could be stock market price prediction, temperature prediction, power demand prediction, okay, water consumption prediction in a given locality. All these are numbers, right? In that case, we are talking about a regression problem, sales forecasting and those things, okay? So this is a single layer network. Once again, I'm repeating, we never count the input layer because the input layer, anyone? Why is this a single layer network? Come on, who has attended my previous session? Give me the answer. Why is this a single layer network? Let me make the session a bit more interactive, okay? So anyone who has attended the session should be able to answer this. Why is this a single layer network? Okay, one answer I see is not correct. Mr. Panda or Miss, there is no hidden layer. That is partially correct, okay. Jairaj, Srinivasan, n-1, but why that -1 is the question here. Only one output node. That is also not technically correct. We do not have output nodes. Shrestha, because there is one receiving node. No, receiving ends are not nodes. Mohsen says one neuron. My question is, why is this a single layer network? Okay. Now that layer can have one neuron, infinite number of neurons, doesn't matter. Okay. But the bigger question is, why is this a single layer? Mayank and Fancy, please post your responses in the webinar chat. Okay. And ask only questions in the Q&A part. Okay. There is only one layer here. Which is that layer? Yes, Natarajan. That is what I'm asking. Okay, there is one layer, but what is that layer? Is the same question I'm asking. Input is directly connected to the output layer. Yes. Input nodes and one output layer neuron for processing. Okay. So why isn't a two-layer network? The same question I'm asking in a different way. Why is it not a two-layer network? Or conversely, if I talk about this, why is this a two-layer network and not a three-layer network? So the same question basically in a scaled manner. So if you see, there are three layers. One is the input layer, one is the hidden layer, one is the output layer. Again, the same question I can ask. Why is this a two-layer network? This is not a three-layer network. Why? Simple answer, I am expecting. Okay, let me give you the answer. Okay, it's a very, very simple answer. Very simple answer. Input layer is never counted. End of the answer. Input layer is never counted. Third time I'm repeating, input layer is never counted as a valid neural network layer. So next follow-up question is, why? Why is the input layer not counted? So here it's a two-layer network. One is the hidden layer, one is the output layer. In the previous case, it was a single layer network. Why? Because the input layer is not counted and you have only one layer, which is the output layer with a single neuron. Correct. So back to the same question. Why do not count the input layer? Exactly. Now I'm getting the right answers because it does not perform any computations. Yes, that's correct. Because it does not process the data. Yes, very good. So I did mention in the last session also that the input layer contains nodes. See, I have highlighted it very clearly. Input layer contains nodes and not neurons. Neurons process the data. So input layer does not contain neurons. It just contains nodes. What is the purpose of the node? Purpose of the nodes is to collect the features from your data set, whichever you are going to use for training. So it will collect the feature values from your training data set and feed it forward for model training, whatever. Okay. So here the only layer is your output layer, which contains a single neuron in this case, and that neuron processes the data. Okay, very good. So same thing happens here. Input layer in this case is containing 4 nodes because I want to have 4 input features. Okay, and those things we have already discussed, so maybe I can quickly revise. The hidden layer contains these 5 blue dots you are seeing. These are 5 neurons. So they will also process. And this red dot that you are seeing is a neuron of the output layer. So only these 2 layer neurons process the data. Very good. Okay, so it's a 2-layer network because you have only 2 layers of neurons. The first layer, which is visible in green, does not have neurons. It just has nodes. The purpose of the input layer is to only collect the data from your data set and feed it forward. That's it. End of the story. Very good. Okay. Now all these calculations we did, so I'll not get into all that. Now here basic question arises, how do I decide the number of nodes in the input layer and the number of neurons in the output layer? So 2 questions again. I'll go question answer basis, okay? So how do I decide the number of neurons in the output layer and the number of nodes in the input layer? Come on, quick. So can we take any random number of nodes in the input layer? Can I take any random number of neurons in the output layer? So yes, very good. So the number of nodes in the input layer, is equal to the number of features in your training data set. Very good. That is the exact answer. So if you have 100 features, you will need 100 input nodes. It is as simple as that. Irrespective of the problem that you are solving. Doesn't matter it is a classification problem or a regression problem or even unsupervised learning. That we will discuss sometimes later. Okay, that's very clear. So the number of nodes in the input layer will be equal to the number of features in your data set. How about the number of neurons in the output layer? Okay, so if it is a regression problem, you will have a single neuron because it has to just predict a single number. It has to predict a single number. Here I'm assuming that we are not predicting a sequence of numbers. That is also possible. That's a different problem altogether. Okay, so then we would be discussing about sequence learning and those other advanced things. Okay, let's stay focused to a simple thing here. So single output single neuron in the output layer is mostly needed for regression problems where you just want to, give a output about, let's say, house prices. That's a single price for a given house features. Okay, or maybe on Monday or tomorrow, let's say, is the stock market going to give you a gap up opening or a gap down opening? Okay. How many points up or down? It's a regression problem. And whether it is going to go up or down, that's a classification problem. So in a regression problem, you just have to predict a single number. So a single neuron in the output layer is more than sufficient. Coming to the classification problems. Now, if you have binary classification where you have 2 labels. 2 labels means cat or dog, Prashant, no Prashant. Okay. Stock market going up or down. It's a binary classification, correct? There are only 2 categorical labels of the output variable. Okay. The target has got only 2 labels. So for binary classification, you can have a single neuron or 2 neurons max. Not more than that. Okay. A single neuron or maximum 2 neurons. If you are using a single neuron, then make sure that your activation function in the output layer is softmax. Okay. That we had clearly seen, I had documented that and even shared that document also on my GitHub. Okay. So that GitHub link, I'll share it once again today. Okay, just stay tuned. At the end of the session, I'll share my GitHub link where you can download the previous session notebooks and notes also. Okay. So once again, I repeat, if it is a binary classification, then we have two choices. Number one, you can use a single neuron. And if you are using a single neuron as the output layer, then the output is a probability for that data point to belong to a default class, which is y equal to 1 typically. Okay. So since it is giving out a single probability, that means a single neuron is sufficient. And then the activation function in the output layer has to be softmax. Okay. Or sigmoid. Come on, tell me. Softmax or sigmoid? Is it softmax or sigmoid? If you have a binary classification, listen to me very carefully. If you have a binary classification with one output neuron, then the activation function in the output layer has to be softmax or sigmoid. Correct. It has to be sigmoid. I have been saying softmax. I was just checking how many of you have attended those sessions and still attentive. Okay, very, very good. Very good. Congratulations. Okay. So if you are using a single neuron for a binary classification, sigmoid is the correct activation function. Now, if you are using two output neurons, that means we need two outputs. And two outputs can be easily given by softmax. In fact, softmax can give you any number of outputs equal to the number of classes. So for multi-class, today we'll discuss one problem of multi-class. Okay. So for multi-class classification, the number of neurons in the output layer will be equal to the number of classes. So if there are 10 classes, you will need 10 neurons in the output layer. If there are 50 classes, 50 neurons in the output layer. Very good. Is that clear? So the number of neurons in the output layer will be equal to the number of classes. Okay. Here I am discussing that, here I am assuming that we are talking about a single label problem. So multi-class, single label. But if you have multi-class, multi-label, then again the problem becomes more complex. Okay. Fantastic. Okay. And what more, we had seen these calculations, how each connection, so from input layer to hidden layer, each of these connections will contain some weights. So the neurons in the hidden layer and again in the output layer will take the input from the previous layer, but not directly use it. So these inputs get multiplied by these weights. Okay. And then a bias term is also added. So what do we say finally? We say that we are passing the weighted sum of inputs to the next layer. You are not passing these numbers directly like 5.1, 3.5, 1.4 and 0.2. That is not perceived by these layer neurons directly. So 5.1 will be multiplied by W11. Okay. And then it gets propagated that way. Okay. So all these numbers, which are my input feature values, will be multiplied by these respective weights. Okay. And then you will have a bias. You will have a bias, one bias for each neuron. Always remember, if there are 3 neurons in this hidden layer, so there are 3 bias terms, B1, B2, B3. And there are 2 neurons in the output layer there. Okay. So how many bias terms will you have? 2 bias terms for the output layer. Very good. Okay. So the same output of the hidden layer neurons. Okay. These are multiplied by additional set of weights. So the output layer neurons receive the weighted sum of inputs from the hidden layer. So hidden layer, whatever is the output, that does not get directly passed on to the output layer. The outputs of the hidden layer are multiplied by these weights V1, V11, V12, V21, V22, V31, V32. Okay. So these outputs are multiplied and then a bias term is added. Okay. So basically, that is how the calculations go, and we have discussed all these calculations in enough detail. So let me skip. This also we have seen activation functions, loss function. So what is a loss function? So ultimately, to train the neural network, you will need some some objective function or some loss function or cost function, okay, which will be minimized. Okay, the whole purpose of training is to minimize this loss function. Okay, and this loss function contains the error of the model predictions. This loss function is containing, I did not say that this loss function is equal to, it is not equal to, it contains that error term, basically. Okay, so what is that error? Error of predictions by the model, okay, during the training purpose. So what we want is, we want to minimize this loss function. Who minimizes it? Come on, next question. Okay, what happens during model training? This is the answer. What happens during model training? A loss function is getting minimized. Okay, that is what happens. So if you are taking 50 epochs for training, in that 50 epochs, the loss function is supposed to gradually keep decreasing. That plot also we had seen, right? But who minimizes this loss function? Next question. Who minimizes this loss function? Okay, so for that we have, so these are the different types of loss functions. Okay, binary cross entropy, categorical cross entropy. So normally we use binary cross entropy for binary classification problems, and categorical cross entropy for multi-class problems, right? KL divergence in the case of unsupervised deep learning, for example, in autoencoders or GANs, where we want to compare two probability distributions. Okay, one of the input and one out of the generated image. Here you are generating images from some latent vector and all. I'm not getting into all that, but basically, KL divergence is mostly used in unsupervised deep learning. That is more than sufficient for now. Okay. So coming to the regression problems, normally we go for mean square error, but there are many other loss functions as well. So same question: who minimizes this loss function, or how does this loss function get minimized? These optimizers will. So if I click on these links, you will directly be taken to. These are all the available losses in Keras. This we have discussed in the last session as well. And similarly, these are all the available optimizers. So what is an optimizer? Optimizer is the algorithm which finds the optimal values of these model coefficients. So model coefficients means these weights and bias terms. These weights, these W's and B's and B's and C's. So there are so many weights, right? W11, W12. So who finds the optimal values of these weights and biases? Which algorithm runs behind the scenes? That algorithm is called as optimizer, right? So different optimizers are available, as I have already mentioned. Okay, stochastic gradient descent, and remaining are all different variants of this stochastic gradient descent. Basically also mini batch gradient descent, RMS prop, Adam W, ADA delta, ADA grad, ADA max, ADA factor, NEDM, that is Nesterov, accelerated adaptive momentum, and so on. Okay, so basically all of them have some momentum term which tends to push your model to better and better learning. So most of the problems that we solve by using deep learning are fairly complex problems. So simple gradient descent is not the right choice. Okay, we need some advanced versions of that gradient descent, and all these guys are nothing but advanced variants of that gradient descent. So optimizers are algorithms which update those parameters of the neural network during training to minimize the loss function. That's what I had said. Okay, and they use some sort of a gradient descent behind the scenes to find the direction of the steepest descent, and then the weights are adjusted accordingly. Fine. And this adjustment of the weights exactly happens during the backpropagation algorithm. I would strongly suggest everyone to go through this page if you want to learn backpropagation. Okay. In fact, I did not discuss backpropagation in detail last time because backpropagation is a very lengthy process and it cannot be just discussed in 10-15 minutes. So Matt Mazur backpropagation, okay, just search. So 90% of the articles which are present on this internet on the planet Earth are somehow derived from this single source. I'm not aware of the articles present in planet Mars and Jupiter, but at least on this planet Earth, 90% of the articles and blogs which are available on backpropagation somehow are related to this. They will use the same numbers, the same diagrams, and the same explanations. So this is the source, mother of all that articles. Okay, so please go through this. Okay, I'll post the link for this article in the chat box. I'll be giving a lot of links, so please keep your notepad ready. Keep on copying. Okay, so this is one of them. And if you are still wondering, this is my GitHub page, but I'll share the link a bit later. Yeah. So this is also done. As I said, backpropagation is the algorithm used to train the neural network, and training means updating those model weights and biases. That's it. So we would not discuss anything more than that. Okay. Now, whether that neural network is a simple ANN or CNN or RNN, some variant of backpropagation is being used. So what I'm not claiming is the same algorithm which you find on this page will be used to train your RNN and CNN. Okay, it is definitely applicable for ANNs. Some variations of that backpropagation is there for specialized networks, especially if it is branching. Okay. So for simple, fully dense networks, simple sequential networks, that is the correct word. For simple sequential networks where the entire data flows in one direction, this is the algorithm which works. Okay. But for RNNs, something, okay, there is another variant of this backpropagation called as BPNN, BPTT, backpropagation through time. Backpropagation through time. So just Google, or you have your ChatGPT anyway, right? You can ask ChatGPT to explain you what is BPTT. That is backpropagation through time and the differences between BP and BPTT. Okay. So please make optimal use of ChatGPT. Okay. Thank you. Okay. Good. Very good. So that is one. Further going ahead. So I am not spending much time. You can see the data flows in the forward direction, that is feed forward, and the weights get updated in the backward direction. That is why it is called as backpropagation. So the weights of the last layer, which is your output layer, will get updated the first. Then the weights of the second last layer, followed by third last layer, and so on. Okay. So the weight updates go in the reverse direction. Fine. Now coming to our topic here. Okay. Before I go ahead, let me give a quick overview of what are images and how does your computer perceive images. Okay. So this kind of slide kind of gives you an overview of the different types of images you encounter on a day-to-day life. Now there are specialized images like DICOM images for medical. So those discussion will not do here. The most common types are black and white image, grayscale image, color images like RGB, which have 3 layers, and CMYK, that is 4 layer images, or what you also call as 32-bit images, normally used in Photoshop, CorelDRAW, or any commercial printing. So all the commercial printing happens in 4 color. Please understand that. They happen in 4 colors. Even in newspapers, have you noticed that at one of the borders, you will get 4 circles, cyan, magenta, yellow, and black colors, 4 color circles. So all the commercial printing, okay, happen in 4 colors. Okay, your photo editing softwares like Photoshop, Adobe Premiere, okay, CorelDRAW, okay, all these work in 4 colors, I would say. Okay, so let's start from scratch. So black and white image, okay, so they have pixel values. So images are composed of pixels. Simple. Images are composed of pixels. So pixels, can we show the pixels? Let me check. Show the pixels. Can you see my screen? These squares. Okay, so sorry about that today. Each square box that you are seeing, my dear, is a pixel. Zooming further and further. Any idea what this image is about? Yes, it is a deer or a stag. Very good. Very good. Looks so you can see the ons and yeah, and this is the face, this is the body, and these are the legs. Fantastic. So you guys, your biological neural network is indeed sophisticated. Okay, and if you see, we have 0 to 32, and then 0 to 31. The first pixel on this corner is 0, and the last pixel in this corner is 31. So 0 to 31 means 32 pixels. Width, and again, if you see, it started from 0 and went up to 31. So 32 pixels height, 32 pixels width. So this is a grid of pixels, and each pixel will have some value. So when I import this data, in Python, I get to see these kind of numbers. Okay. So, so each pixel has got some number between 0 to 255. Okay. Typically. Okay? 0 to 255. And there are 3 planes for a color image. So for a black and white image, it's just a single plane with the value as 0 or 1. If the pixel value is 0, where any place, if the pixel value is 0, that's a dark pixel. That's a black pixel. And if the pixel value is 1, that becomes white. So that's how you can interpret a black and white image. Okay. In grayscale image, the pixel values will range from 0 to 255. So essentially, you have 256 shades of gray. If the pixel value is again 0, that represents a completely dark black pixel. And if the pixel value is white, it represents a, if the pixel value is 255, it represents a white pixel. Simple. RGB, that is, there are 3 planes. If you see, this is the color image, and this is actually composed of 3 layers. One is the layers of pixels, basically. So this is the red layer, green layer, and blue layer, and each layer will have pixels once again, as I have shown in this image also. So what you are seeing is a composite image. But if I decompose this, I'll have 3 layers, okay, clearly. So this is the red layer. This is the green layer values. These are the blue layer values. Okay? And that is for one image. Okay. That's a dot means there are many more values in that. But you can clearly see this is for one image red layer, one image green layer, one image blue layer values. Actually, these values are normalized. That is the reason normalized means divided by 255. And that is the reason you are able to see as fractions. Okay, but the original pixel values were in the range of 0 to 255. Let me see if I have that. No, it's already normalized as of now. So if you see, this is 32 pixel by 32 pixel cross 3. Why 3? Why 3 here? Why 3? Because there are 3 planes. Okay, and this data set which I am showing right now is CIFAR 10 data set, which is one of the most popular data sets for beginners learning, CNN, OpenCV and all that. So I just copied one of them and saved. So deer, where is that deer? Yeah, these are the deer images. Okay. I just right clicked and saved one of the images. Each image is 32 pixel height, 32 pixel width, the 3 planes. And for each plane, the pixel values are in the range of 0 to 255. Okay. So now listen to me carefully. So since there are 3 planes which are of 8 bits, 8 multiplied by 3 becomes 24. So this color image that you see is a 24-bit image. It's a 24-bit image. Now there is one more type of image, what we call a CMYK color scheme. Okay, that is cyan, magenta, yellow, and black. Initially it was red, green, blue, and now we have 4 channels. We can say 4 planes or 4 channels. And each plane is again 8-bit. So 8 into 4 becomes 32-bit. So like paint, BMP, okay? That is again 32-bit images, and that's why TIFF, TIFF format is also 32-bit. Okay, your JPEG, JPG, or GIF, these are RGB. But once you convert that into TIFF, TIFF format, that becomes 4 color image, okay? So they will have 4 planes of pixel values, 4 planes. Just now I showed 3 planes. Once I imported that image in my Jupyter, I just now showed you that it has got 3 planes, and you can also look at, just see the shape. So there are 50,000 images in the training set, 10,000 images in the test set, and each image is 32 pixel by 32 pixels and having 3 planes. That is how this data set is all about. Okay, it's clearly mentioned here. So in total, you have 60,000 images, 50,000 in training, 10,000 in testing. Perfect. And they are divided among 10 classes. Which are those 10 classes? Airplane, automobile, bird, cat, deer, dog, frog, this and that. Okay, these are your 10 and you can follow. Okay, so this is the basics about how an image is. Okay, I hope there is no doubt. Now, what I'm going to do is I'll start with a simple project directly, and from there I'll start explaining stuff. Okay, so instead of directly taking just theory. So first I'll start with one of the most basic and most common data sets, which is your MNIST handwriting digit recognition data set. Here, I'm not taking a very sophisticated data set because my focus is not to solve a real world problem here. My focus right now is to teach you what CNN is all about, why is it needed, and what it does. That is the only takeaway from this session. If you understood why do we need CNN, how actually they are working behind the scenes, I can actually pull out the layer weights and show you. I'll print those layer weights for you. Okay. So that is more than sufficient as a takeaway from this session. Okay, ready. So what I've done here is, okay, again, so this code is running on a cloud environment provided by Jarvis, and this is running on a GPU RTX 5000, and of course it's not free, so don't try that. This is 32 GB RAM and there are 7 cores. Okay, so that is the machine which I'm currently using to train my model. So my model training will happen very fast. And when you run the same code in your local machine, maybe by using Colab or local environment which has TensorFlow pre-installed or installed, okay, it might take some time. Okay, so don't compare the speeds at all because I am running a GPU, a heavy GPU, a paid version of that GPU. Fine. So the usual imports are there. So as I said, I'll be loading this data set from Keras. Keras already has built-in data sets. So if you want to search Keras built-in data sets, as IMDb data set, fashion MNIST data set, okay, IMDb data, sorry, this, CIFAR 10, CIFAR 100, fashion MNIST, Reuters, and Boston, okay. IMDb for movie review sentiment analysis, I think I mentioned about this in my NLP sessions. Again, this is for text-based classification. This is a regression problem you can use, okay. Fashion MNIST is again, image classification data set, and all these 3 are image classifications. MNIST is what I am using currently, and you can take the same code and actually do this same exercise using CIFAR 10 and CIFAR 100. These are also benchmark data sets in a way, but not too much. And apart from that, I would suggest you to also explore another data set, GTSRB, German Traffic Sign Recognition Benchmark Dataset. Okay, GTSRB. That is also a very fantastic data set. You should explore while learning CNNs or going to YOLO, SSDs, and a number of other things. Okay, so these are some benchmark data sets. You should make yourself comfortable with these data sets, and you have to make sure that you are able to make a model and do the predictions on these benchmark data sets before taking up any sophisticated project. Okay, so which one? Start from MNIST, go to fashion MNIST, second thing. Third, go to CIFAR 10. Fourth, go to CIFAR 100. Fifth, go to this GTSRB. If you are done with these 5 data sets, means you're thorough with the basics of CNN and how that entire deep learning actually works. Now you are ready to go to the next level, okay, object detection, object segmentation, and number of feature engineering, feature extraction on images, OpenCVN. So those are secondary. This is primary. These at least 5 data sets. You should be very, very thorough. Okay, you should be able to make these models, literally blindly. You should be thorough to an extent that you can literally dictate, or not just dictate, you can just orally dictate the code to anyone. Okay, you use this, then you do this, then you do this, you do this, and then you'll get a model. So literally that level of confidence I want. Okay, let me take a quick, not a break, but there are some questions in the chat box. Let me just check. Lalit is asking, so we mostly use RGB. We don't use, it is basically your computer prefers to use RGB because of smaller memory requirement. Okay, so the same information can be contained in lesser memory because you need only 3 planes. Until unless, see why I said all the production or the commercial printing. So suppose you are talking about an image of an actress, which let's say, which you want to enlarge as a poster and print it, which is like 20 feet by 80 feet. Yeah. So 20 feet height and 80 feet wide. Such large billboards. Have you seen very, very large billboards having big, big posters of, models? Okay. And they're very crystal clear, very crisp images. Now, those crystal clear, crisp images are not RGB images, my dear. That's what I meant by commercial printing. So all the commercial printing needs CMYK. Okay. Reason. This is a simple reason. Simple reason is you have more color depth. How many colors can you have? 2 to the power of 32. Right. It is as simple as that. Okay. So you have more color depths, more color variations, more number of colors possible, literally. Yes, that is why 32-bit images are so popular. But one image will be in GBs. Okay. So that is one drawback. So until unless we are not talking about commercial printing, your normal RGB, JPG image, GIF image, they are more than sufficient. So normal, photo that we are shooting on a day-to-day basis, selfies and all, JPG is more than sufficient. Okay, unless you are shooting, for a model and all that. Perfect. We need to take real MNIST data set, which is very difficult. You will have to, Ashwin, first create such data sets. People are doing that. Okay, and they have done for different Indian languages. If you search, all these data sets are now freely available. Okay, so don't worry. The reason I'm taking a simple data set is my focus is not on solving a real world problem. Again, I am repeating. Okay, my focus is to teach you how CNN works. Okay, so the entire session's focus is on CNN, not to solve a real world problem. So I'm not going to take a real world data set and get into more problems. Okay. Okay, Christopher, yes, absolutely, you're correct. For all magazines, newspapers, commercial printing, CMYK is primarily used. Very good. Now on the Q&A side, I see questions like Fancy is asking which algorithm is suitable for classifying potato diseases. Any classifier? CNN. It's a standard disease classification. So you might need the raw data, which are like different images of potato having different types of diseases. Okay. And then you use any standard CNN. That is more than sufficient, I think. Yeah. Only thing is how you tune that network is very important. So maybe I am planning to take one more session on optimizing the neural networks. Okay. Or tuning the neural networks. That's a different art altogether. So creating neural network is easy, but optimizing it for best performance, that is a different art altogether. Okay. So that is done. Dinesh is asking, what is the link between optimizer and loss function? So that is what exactly I answered. Optimizers will find the minimum value of the loss function. And then Ashwin is asking, what is the difference between optimizers and optimization algorithm? Same. Same. It is exactly same. Don't worry. Optimizer is same as they are synonymous. Same. Ditto same. There's no iota point of difference. limit iota tending to 0. Okay. So they are exactly same. Some prefer to use the word optimizer. Some prefer to use the word optimizer algorithm or optimization algorithm. Okay. How backpropagation works in RNN versus LSTM and CNN. So exactly that's what I said. I'm not going to discuss backpropagation because that's a lecture of its own. So for now, I'm going to pass that answer. Pass on to ChatGPT, in fact. Okay. Dharvi is asking, sir, about audio signal processing. Can we use CNN? Yes, very much. CNN is used to extract features. I'm spilling the beans here, okay, slightly. Okay. So it can be used. Done. So my question answer panel is empty. So let's continue now. Back to that code. So I imported TensorFlow dataset that is loaded. You can see 60,000 images. So let me just click on this. This is the data set. So it has 60,000 images, 28 pixel by 28 pixels. It's a grayscale image. So it has only, can you tell me how many planes will I get? It's a grayscale image. So how many planes? Come on, you have been following this. Grayscale image will have how many planes? Very good. It would have a single plane. Very good. Very good. And 10 digits and 60,000 images for test set. Very good. So test is also 10,000 cross 28 cross 28. So you see the size and the shape of the data set here. Okay. So the first index gives you the image number. And then the next two dimensions, sorry, not the index, but the first dimension, I would say that is the correct word. The first dimension is the image number. And then the second and the third dimensions of that data set is your actual image, the width and the height. And see the data type is uint8. It's not unit. Many people read it as unit. It's unsigned integer 8-bit and signed integer 8-bit. So each pixel value will be in the range of 0 to 255. I think that is very clear. 0 refers to black, 255 refers to white. You can see. Now the intermediate values are the shades of gray. Now in this case, what we have is 28 pixels by 28 pixels. So each image now contains how many pixels? 784 pixels. Is this clear to everyone? Right now, we have 784 pixels per image. 28 pixels width, 28 pixels height, right? That is my data set. Very good. So it is important to understand what data we have in hand before, starting to run any algorithm over it. Okay. So now I am showing the first image. I'm just showing the first image after importing. Can you see zeros, some numbers? These are whitish pixels, zeros are blackish pixels, you can say. Yeah, this is how that image comes up in Python. And that is mostly non-comprehensible to a human. But machine understands these numbers, right? Now let me do a simple thing. Using a color map, gray color map, I am going to print that first image. So that looks like 5 or something. Let me change this to 10. This looks like 3. Let me change this to 100. This looks like maybe 5 once again. Or yeah, maybe let's 1000. This is 0 indeed, and so on, right? So I'm not having any axis. False means you don't have axis, x-axis and y-axis. So that is how you are printing, okay, or plotting rather, that is the correct word. You are plotting the images without the axes. And that's how you are able to generate this. Simple. So what you are passing is the index of the image and use a gray color map. That's it. Fine. So this is how you can visualize each and every image just by changing that index. And what was that? 1000 image. So let me get the index of that 1000 image. Okay. So you see the label, sorry, not the index, the label of that 1000 image is 0, which is, okay. So I think this is very clear. So right now each image is 28 pixel by 28 pixels. And I am going to reshape it. I am going to reshape it to 1 cross 784. This is called as flattening operation. This is called as flattening operation. Okay. Why am I doing that? I'll just now show you. So there is a question. Joanne is asking, are there Python libraries focused on facilitating the process of finding the best model focused on See, there are auto ML libraries, but still huge amount of manual intervention would be needed. And if you are doing grid search or brute force search, it's hell actually. Okay. So mostly people will use either Keras or PyTorch. These are the two most popular frameworks to create your neural networks, including CNN or even RNN or even LSTM, autoencoders, GANs. These are the most common frameworks. But for advanced things like transformers, there is one library called as transformers, another library called as Hugging Face. So they contain pre-trained models. Okay, so we'll talk about them sometimes in some other session. Okay, so what I'm going to do is reshape each image into a stream of pixels, what we call as a row vector. Okay, think about this 2D image. It's a 2D image right now because it has length and height. Okay, so I'm going to reshape this into one dimension. I'm going to reshape it into one dimension. Okay, all the 784 pixels. So exactly this is what I was trying to show you in this. So just imagine this is your 28 pixel by 28 pixel image, which I am flattening this way. I can flatten it this way or I can flatten it this way. So mostly we flatten it as a row vector, not as a column vector. Okay, right now this image shows it as a single column. I will flatten it as a single row. And that is why, see, the shape is one row, 784 columns. Now, what I'm trying to say is, please listen to me. Each pixel will become a feature. So each pixel value will become that feature value. So how many features do I get for one image? Come on. How many features do I get for one image? Perfect. So 784 features I am getting. So now, did you understand what is this? So 60,000 images, and each image is reshaped to 1 cross 784. So why is this 60,000 cross 784? Because each image is being represented by its pixel value, which is in one row. Okay. So how many pixel values I have? 784 pixels. And so I have 784 features. Same number of features in the test set also. Only the difference is the number of images in the test set is less. Okay. So basically each pixel is being treated as a single feature. Perfect. Any questions still here? All good? So now you can see the numbers, 784 numbers. These are all 784 numbers for one image now. Okay. The next thing I'm going to do is convert the data type for both training and testing. Any idea why I'm doing this? Any idea why I'm doing this? Why is that needed? So normally it is a good programming practice. Normalizing, no. We will be normalizing it later. Correct. So see, right now the pixel values are integers. Please listen to me carefully. The pixel values are integers. Okay. And when later on I am going to use these pixel values for calculations and computations, I do not want to lose precision. So first thing is you convert these integers into floats. So later on, whenever you are doing any normalizing operation or any other image processing operation later on. So what are the image processing operations? This is something what we call as image data augmentation, which I'm not going to discuss, of course, because of time constraint. So image data augmentation, just do a Google search or ask ChatGPT, what is image data augmentation and what are the techniques to do that? And how do you do that? It will also give you the Python code. So you can zoom into an image, resize the image, make it smaller, bigger. You can rotate the image. You can share that image also. Okay. So you can create additional images. Okay. Augmentation means you are adding additional images which look similar to the original ones. Okay. So now your data set, instead of having 60,000 images, might have 80,000 or 90,000 images. And these 30,000 images have got generated additionally by doing some of these resizing, zooming in and out, and shearing operations, okay, or even rescaling, shifting the image. So doing some manipulation with the existing images, because maybe in real life there are always surprises. Okay, changing the illumination, yes, changing the illumination of the images, making it lighter, making it darker. So these are the interventions that you would be doing, and all of these interventions that you are doing on that image is called as image data augmentation step. Okay, so that I'm not doing in this example, in this notebook right now. I hope that is clear to everyone, right? So before you do any of those image data augmentation, okay, it is mandatory that we should upgrade the pixels from integers to float, so that we do not lose precision when any of these operations are performed. Losing precision directly correlates to losing information. Okay, you don't want the pixels to lose their information. So that is the main reason we have to upgrade it. And then I'm normalizing it, because again, neural networks normally expect the data to be within the range of 0 to 1 because of multiple reasons that we'll discuss sometimes later. It can pose a problem during backpropagation, exploding and vanishing gradients, and a number of things are there. So mostly the exploding gradient is a problem. Okay. Vanishing gradients is a bigger problem in LSTMs, in RNNs. Okay. So those are additional problems with training, and to tackle those problems, it is normally advisable that you normalize your data. In this case, how do I normalize? All the pixel values are converted between 0 to 1. That's what I did here. By dividing, now I'm printing it again. You can see that the pixel values are scaled to 0 to 1. Scaled between 0 to 1. Correct? Perfect. Perfect. And you see the data type has been upgraded to float 32. Perfect. Perfect. Okay. Right now, your Y train is a integer. Right now, your Y train is an integer. Now, let me plot. Listen to me very carefully. This is going to be mind-blowing. This is going to be mind-blowing. What am I plotting? Can you guess what am I plotting in this block of code? What am I plotting? So what was the image which I plotted? This is 1000. Okay, I'll use the same index just to bring in consistency. So I'll just change it to 1000 here. There is something maybe. Or but what are we plotting? Just give a thought. What are we plotting? No responses. Lalit, yes, very good. We are plotting that flattened image. Very good. Absolutely correct. We are plotting that flattened image. And if you see, it's a streak of zeros. You see the numbers, right? Initially, we have how many zeros? Roughly maybe 200 zeros are there. Then followed by some numbers. And then again you have zeros. So and then some numbers and mostly zeros once again. Okay, these pixel values, and that is what you are plotting. Okay, so those number of 200 zeros will become a streak of black, and then non-zero values are in grayscale. I've zoomed as much as possible. So these non-zero values are in grayscale. Can you see? These non-zero values are in grayscale. These non-zero values are in grayscale. Okay, so what are we plotting here? That is the flattened image. And why are we doing this? Acha. Instead of answering that, rather I'll ask another question. Can you identify which digit is being plotted here? Can you identify which digit is being plotted in this flattened image? Come on. Can you identify, can you as a human being identify which digit has been plotted here? What is the handwriting digit? Is it 0 or 1 or 2 or 3 or 4, 5, 6, 7, 8, 9? What is the digit being plotted after flattening? What digit is present in this flattened image? digit, handwriting digit. The pixel values are between 0 to 1. So do not get confused. No, it's not one digit. See which digit I said, not how many digits. This entire image got flattened, but that image which got flattened, that image represented which digit? Can you identify? What was the original image about? So when I'm asking this. So here you can identify it as 0, right? You can identify this as 0. Yes or no? Come on, tell me. You can identify this as 0. But if I flatten this in this format, will you be able to identify that it is still 0? Will you be able to identify that it is still 0? Do you think any superhuman can do that? Do you think any superhuman can do that? Do you know about any human on this planet Earth currently existing, forget about the Marvel series, who can identify that this flattened image corresponded to 0 before flattening? Even Rajnikant cannot, okay? You cannot even identify a QR code. Very good. Yes, that's a 2D. Forget about identifying a 1D. Now, that's another level of complexity. That's a different thing. This is simple one dimension and you are not able to identify. It was identifiable in 2D, but in 1D, to a human, this has become completely useless. Now, the last question is, before I go ahead, do you think the machine will be able to identify this as 0? Do you think the machine will be able to identify this as 0? Come on. Anything which you are not able to do, you are expecting the machine to do. A problem which you are not able to solve, you are expecting the machine to solve. Is that a fair expectation? So Dharvi says it contains features for that image. So yes. So now I've got mix of zeros and ones. Yes and no's. It will identify the pattern. But Lalit, where is the pattern? You flattened everything. Pattern is gone. Okay, let's, I'll not give you the answer right now. Okay, but if the machine is able to identify this, okay, let's say, what would be its accuracy? What do you think? 30%, 40%, 50%, 80%? What do you think? What would be the accuracy of the machine? Let me give some numbers. 30, 50, 60, 80, 90. What number do you think? 90%. Okay, very good. Then you don't need CNNs, frankly. If the machine is able to identify this, you frankly don't need CNNs. End of the story. I mean, this data was not needed. Okay, but somehow people do agree that machine might be able to solve, because even though you are flattening the images, okay. Let's see. So what I'm going to do is converting this into categorical. What am I converting this into categorical? The Y train, which was currently an integer, I'm doing a one hot encoding. Please understand. This is the function in Keras to do one hot encoding of Y. Right now, Y is a single column. Come on, listen to me carefully. Y is a single column. Okay, and that label is an integer from 0 to 9. That I am converting into 10 columns, doing a one hot encoding. Okay, so doing a one hot encoding, and now you see that each this -1, what was that -1 initially? That -1 was 8. Now that 8 is represented by a sequence of 10 numbers. It is represented by a sequence of 10 numbers, and you have a 1 in the 9th position because it starts from 0 to 9. Okay, so there is a 8 represented by this vector, I would say. Okay, so it's a one hot encoded Y now. Okay, that is one step. So basically your Y column is now represented by 10 columns, and that is why you would need 10 output neurons. Okay. This is clear. Let me create a fully connected network. So sequential, everyone understood from the previous session. And I'm going to use dense layers. What are dense layers? All the neurons in the current layer are fully connected to all the neurons and nodes of the previous layer and all the neurons of the further layer. That is what is a dense layer. Okay? And sequential means data flows in one direction. Okay, forward or backward. I mean, there is no branching. If you want to create branched networks, sequential class will not help. This is a sequential class. You will have to use the functional API. So I'm just clearing the session. Sorry. And just let me execute. So what I'm having is first hidden layer. Please understand, the first hidden layer has got 64 neurons. Input dimensions for the first hidden layer is equal to the X trained shape 1. So this is going to be 784. This is going to be 784. So input dimensions will be 784 input nodes. And the activation function, again, as I have mentioned very clearly in my previous sessions, until and unless you have any strong reason, do not use anything other than ReLU. Only for the output layer, I'll use something else. For all the other layers, I'll use ReLU. Simple. So this is ReLU. And then second hidden layer, third hidden layer, fourth hidden layer, and the fifth layer is my output layer. So how many layer network is this? How many layer network is this? 5 layers. Okay, 4 hidden layers and 1 output layer. Output layer has got activation function as the softmax. And why 10 here? Come on, tell me, why 10 here? Because we have 10 class labels, right? Categorical cross entropy is my loss function. Optimizer, you can experiment, RMS prop, Adam, add, and so on. Metric here I'm using is accuracy. Simple. Okay, very simple problem. Okay. And okay. Now let me print the summary of this model. Okay. Now why is this 50,240? Those calculations I have done. So I'm not going to repeat all that. So there are 784 pixels. 784 pixels multiplied by how many connections? 64 connections. And then there are 64 bias terms. Perfect. That's how you get 50,240. Is that very clear? Now from this first dense layer to the next dense layers, how many connections are there? How many connections are there? This is 64 times 64. That many connections are there, plus 64 bias terms. Once again, how many? 4160. Beautiful. This is why this is 4160. And that's how you can start continuing all the calculations. Total 57,000 parameters are going to be trained in this case. Okay. I'll not do the training. It might take some time, but during the model fit, you are passing your training data and Y, which is categorical or one hot encoded now. Batch size I'm taking as 128, 10 epochs I'm going to run, verbose to print out all this training output and validation split. So out of that 60,000, 20% of that data will be head for validation. Okay. So now I'm going to plot the validation accuracy and the training accuracy. You can see there is an overlap here, and beyond that, the difference between validation and the training is increasing, which directly hints overfitting. So your model is overfitting beyond, I would say, third epoch. So beyond this point, your model is overfitting. So this is roughly your third epoch. On that, I would say it is fitting. Okay. And you have already reached roughly, can you see? You have already reached 96% accuracy. 96% accuracy, man. 96%. Someone was saying 86%. So your brain cannot even process this data. Forget about being able to recognize. This is completely useless for a human being. And now your machine is able to recognize this by 96% accuracy, you see. And this is the strength of basic neural network. Then why do we need advanced neural network like CNN? Okay. So simple reason, okay, is that, yeah, so you can see your model evaluation test accuracy. So one problem here that I'm facing is the way that we did is not a scalable thing. What did we do? We flattened that image. That is not advisable because we are ignoring the information which is present in the pixel positions and the correlation of the pixel values with their neighbors. So neighborhood information is lost. basically. Neighborhood information and cannot handle translation. So if I rotate the image and again do a flattening, that is completely gone now. Okay. So image translations, rotations, zooming in, zooming out. If you do any of these operations on the image and then you train by flattening it, of course, that simple ANN will give you a very bad accuracy. But that is the biggest idea behind the CNN. CNN is able to take an image as an image. Please understand that that is the last statement. CNN is able to take an image as an image. The way we see it, the computer sees that way. You don't have to flatten it. You can directly feed a two-dimensional image. You can directly feed a three-dimensional image. You can directly feed a four-dimensional image. That is the beauty of CNNs. Okay. But how does it learn? Okay, let's take that quickly. Okay, I think I have some notes which I can share it. Okay, I don't have PPT, but let's discuss it from here. Okay, fine. So now I'm going to use convolutional neural networks on the same data set. Convolutional neural networks on the same data set. See, code-wise, there is only one line of code which is going to be different. Code-wise, two lines, not one, two lines. One for the convolutional layer and one for the pooling layer. That's it. So only two additional layers will come up, and they are not additional. They are going to substitute two layers which are existing. So we had 5 layers right now. One was the output layer, 4 hidden layers. I'm going to substitute 2 of the hidden layers with convolutional layer and a pooling layer, the same network. Okay. So code-wise, it's not going to be anything different, okay, except those 2 lines of code, okay, where I'll be replacing 2 hidden layers with one as a convolutional layer and one as a pooling layer, right? So don't worry about the code. Okay? But what are we doing? Let us understand that quickly. It's very simple, okay? So using the convolutional neural network, the spatial arrangement means X and Y. Coordinate, okay? Spatial arrangement of the pixels is retained. And that is what we completely destroy it by flattening it. Now, what does that mean? Spatial information is retained means what? What does that lead to? That is nothing but the relationship between the pixels, okay, with their neighborhood. So see, if I just give you nose, can you identify if this is Prashant or not? So if I place my nose here, or if I place my eye somewhere here and the other eye somewhere here, will you be able to identify me? Yes or no? Come on. So not possible, right? Yes? It's very difficult. So, but if you are looking this face as exactly this way, the eyes are above, then in between you have the nose, below that nose you have the mouth, below that you have the chin, and this is the structure of the face. These are the places where you have the ears. That way you can recognize this is the human face, and that human face belongs to Prashant. Let's say, so that is what information learned by the CNNs. Okay. So now let's take a standard CNN model. The current ANN model. The current ANN model, what did we do? Let's say the current ANN model, which we were just now discussing, what did we do? We took a 2D or a 3D image. Okay, right now we took a 2D image and then we flattened it. There is a function in TensorFlow or Keras called as flatten. We can actually use a flattening layer. That's a layer which can do the flattening. Right now, we did the flattening operation explicitly by using NumPy operation. But if you want, you can actually do the flattening operation by using a special layer in TensorFlow or Keras. Essentially, you flattened it, and then you had fully connected layers. You had 3 or 4 fully connected layers, correct? You had 4 fully connected layers, which are hidden layers, and then finally an output layer. So this was your neural network architecture as of now. Now, what I'm going to do is take an input image as an image, pass it to a convolutional layer, okay, followed by a pooling layer, okay. And then this process can be repeated 1 or 2 times. So what we call as CNN layer in general, okay. So I can have multiple CNN layers. So convolution pooling can be repeated multiple times, okay. Somewhat like this. So convolution, 2 times convolutions followed by pooling. Even this can be done. So that's what I said here. So it's not mandatory that you do the convolution immediately and pooling. You can do back-to-back 2 times convolution and then pooling. But what is convolution and pooling? I'm going to discuss that. But you see, these are the kind of architectures which people use. So 2 times convolution and then pooling, and then repeat that 3-4 times, and then followed by the dense layer, and then it goes to the output. This is a state-of-the-art architecture called as VGG16. Visual Geometry Group is there, VGG16. And if you count, there are 16 layers in this. Want to count? No, you would not be counting the pooling layers. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. And that is why this is called as VGG16. And there is another variant called as VGG19 also. Okay, from the same. So maybe sometimes later we will discuss about that. But we do not count the pooling layers for a reason. I'll tell you. Okay. Back to that notes. Someone is last time notes. It is shared. Ashwin, please go to the GitHub link. Everything is shared. Okay. So I'll share the GitHub link at the end. Don't worry. It's all there in my GitHub link. So I'm going to use some convolution and pooling, followed by, now this is important, followed by flattening. I'm still going to do flattening. Please listen to me. I'm still going to do flattening, but after some convolution operations. Okay. So I think here it was not mentioned, but listen to me carefully. There is a flattening operation here also. Okay. Then followed by a couple of fully connected layers. Just now, as I said, these are dense layers, means fully connected, and then followed by an output layer. This is the network architecture that we have. I'll take half an hour more. So if you are in a hurry or really hungry and take a break, I'll continue. But the bigger question is, why do we need these convolutional layers? And answer is very simple. Okay, we want to extract the right features from the image. So who is responsible for feature extraction? Who is responsible for the feature extraction? The filters. So convolutional layer extracts the features. But how does that extract the features? By using filters or kernels. Once again, I repeat, what is the purpose of the convolutional layer? I'm using convolutional layer to extract the right features from the image. How is that done? That is done by applying appropriate filters. You are going to apply. The machine is going to apply. Okay. But you are going to configure that filter or kernel. Okay. It is, both are similar analogous terms. Okay. So sometimes it is called as filter, sometimes it is called as appropriate, APP. So how does that work? That I'll show you. Process of applying a filter onto the image. So if this is the image, listen to me, and there is a filter. So can I take an object? I've got an object. This is my filter. This is my filter, and this is the image. So I'm going to apply so just imagine that there is some paste over here, and I'm just applying the paste on my image, but line by line, like this, slowly. Okay, it's not like this. It's not like this. Please understand. Okay, so this is my image. This is my image, and I am going to start from this point. Okay, so slowly, this is one, and then I'll start from here. Again, this is next, and then further down. Okay, and then that's how it keeps on going. You don't apply it this way. It applies sequentially. And this process of applying the filter, this is my filter, this is the image. Okay, the process of this applying application is called as technically convolution. Okay, it's that simple. So whenever I say you convolve the image with the filter, means you are applying the filter on the image. And what does that lead to? Come on, what is the output? The output is features. We don't call it as features, we call it as feature maps. I'll show you. So can you see this is the filter that you applied and you ended up with something called as feature map. This is the original image, okay, and you are applying a feature, and what you ended up is with a feature map like that. So that is what your computer sees in the next layer. This is the first input layer. Input layer, it was the original image. In the next layer, what you have is now the feature map. Okay. So this is what you would get by applying the filter. So what is happening technically? I think I have got something here. Okay. To show. Yeah. So basically, if this is a filter, this is a filter. These numbers represent, maybe I can take a simpler example. Yeah, this is a simpler example for all the three channels. Can you see these? So this is my filter, and these are the pixel values. These are my pixel values. Okay, these are my pixel values. So what I'm going to do is I'll multiply the pixel value with the filter value. Let's say this. So this value gets multiplied by this. Then this value gets multiplied by this. The next one is this value gets multiplied by this, and so on and so on. Okay, and you will get some number total. Multiply and add, multiply and add, multiply and add, multiply and add. So you are multiplying this, and everything you are adding. So this is what you get from the first channel. So if it's a 3D image, okay. So if you have a black and white image, then these channels will not be present. It is as simple as that. But if it is a color image, then you'll get 3 channels, right? So this is my red channel. Same operation goes in the second channel. Same operation goes in the next channel, okay? So this pixel value gets multiplied here. This pixel value again gets multiplied there, and so on. And after every multiplication, that product gets added. So aggregated. I might have that also somewhere. Can you see? And then finally normalized. Finally normalized means what? Finally normalized means what? See, I cannot tolerate 300 and now you can see these moving as well. Can you see this moving? I was wondering why is it not moving. You see, this is your exact convolution operation. Starts from here, and all these multiplications, and these numbers are also updating. And there is one bias. And finally, you can see the output. This output here is a feature map. Please understand, this output here is your feature map. It's a feature map. Okay. So Lalit, fantastic. You are very, very correct. So since this is the RGB image, so the kernel or the filter also needs to have 3 channels. Very, very good. Very good. So for a 2D image, you need a simple 2D kernel. And for a 3D image, you will need a 3D kernel. Very good. Very good. For a 4D image, let's say CMYK image, you will need a kernel which has got 4 layers. So it's a 4D kernel then. It's a 4D matrix. Simple 4D NumPy array. Simple 4D NumPy array. Is that clear, everyone? So you add all these numbers and then divide this by the total number of pixels. So in this case, how many pixels you have? 9 plus 9 plus 9. So 27. That total product you divide by 27 now. Okay. So then that number you will get. So right now this is not normalized. Later on, normalization of the feature map will happen. So I am just putting the numbers over there, but later on the normalization will also happen. Okay. Normalization can be done at once. Okay, because that's a vectorized operation. You can normalize the entire feature at once. Okay. So that's how it goes. Okay, you are multiplying and adding the feature values, and then you are able to generate the features. As I said, there is one more thing. Okay, let me show you something very interesting. Okay? Again, this is one image I got. Sorry, yeah, this one. So now, these are, I would strongly suggest everyone interested in computer vision to also study something called as image processing. Image processing, okay? There are several books. I personally like Anil Kumar Jain's book on digital image processing, okay? That is one book I seriously like. And the other Bible of digital image processing is your Gonzalez. Gonzalez and Woods. Okay, so in these books, you will get some predetermined filters. What do you mean by predetermined filters? People have experimented. So this filter, if I convolve, listen to me carefully. If I convolve this filter on this image, this is the resultant. Can you see? Edge enhancement has happened. Edge detection has happened. So this is an edge detection filter. Similarly, if I convolve this filter with this image once again, can you see this operation? This operation is called as convolution operation. This is the convolution operation. It's not multiplication. It's a convolution operation. So when I convolve this filter with this image, what I get is a sharpened image. And how did I get this? This is there in your Wikipedia. I just copied from Wikipedia. So just search Wikipedia and filters for images, standard filters for images. That is from where I just copied. So these are standard filters available. And where are these mentioned? Those two books which I mentioned, Anil Kumar Jain's Gonzalez. Okay, those are standard digital image processing book. Any standard digital image processing book will have all these filters mentioned. So as of now, you can see these filters are two-dimensional, 3x3, 4x4, 5x5, and something like that. Okay. So for sharpening, for blurring, can you see here blurring? We can even do blurring. See, this is a blurry image. We can sharpen it. We can detect the images. So a lot of things we can do only by applying right filters. But the bigger problem that we are facing right now is we expect the neural network. Listen to me very carefully. This is a standard knowledge base available to us. This is a standard knowledge base available to us. This we have been knowing since last 50 years. Not joking. Filters were already available to us. But now what I'm doing is I'm initializing the filters with random numbers. Listen to me carefully. That is exactly what is happening. I'm initializing my filters with random numbers, and during backpropagation, I'm updating these numbers. And I'm expecting that at the end of 100 epochs or 50 epochs, these numbers will converge to these. That doesn't happen so easily. Okay, that is the problem most people face. Okay, when their network is not giving good output. So we already had these standard filters, but I'm not using these filters, unfortunately. Okay, I'm expecting that these filters will be generated, not generated, but the values will be updated during the backpropagation step. Okay, so that it can solve my problem. Okay, so that it can solve my problem. What problem are we solving? Simple image classification. So coming back, so convolution is the process of applying. How does it apply? I have shown you. The output is called as feature map. I have shown you. Filter can be 2D or 3D. So 3x3 filter I have shown. Similarly, you can have 5x5, 7x7. You can have 11x11. We normally prefer to have odd side shaped filters. We normally prefer to use odd shaped filters. There is a question I was asking, how do we get these filters? You don't get it. You just specify what filter you want, and these numbers are randomly generated initially. These are randomly initialized numbers. Randomly initialized numbers I've repeated for the 5th time. And these randomly generated numbers will get trained, updated during backpropagation. Right? So the first filter that is randomly generated, listen to me carefully, the first filter which got randomly generated will extract random features. Completely useless features in the first epoch. But the filter got updated. That updated filter will give more meaningful feature in the second epoch. Then it again get updated. More meaningful feature in the next epoch. Filter gets further updated. Updated. Now after 100th update, the feature which is being extracted is to the point, is precise. Exactly that is needed to solve my problem. Is that clear? So you initially start with some random numbers. So features which get generated are random features. So the error will be very high. Error will be very high, right? Your prediction error will be very high. And then the model will update those features. Features means, sorry, filters. And then updated filters will extract better features, more meaningful features, more discriminative features, more informative features in later epochs. Yes, is that making sense? Is that making sense? Right? That is what is happening. So you do not specify those numbers. Numbers are being learned by the backpropagation step. Okay? Perfect. So three-dimensional filters for 3D images, two-dimensional filters for 2D images. It is as simple as that. Okay? So you take a 2D filter for a 2D image, 3D filter for a 3D image. Next. Actually, I did not want to discuss this. Can you tell me, can I consider image as a signal? Normally, you see signals as these. Can I consider image as a signal? What is your thought? Okay. To be precise, the word convolution is a signal processing concept. It's not an image processing concept. So if you go to Wikipedia and search for the word convolution, the very first word in that article will be in digital signal processing. Convolution means so and so and so and so and so. Okay. Images are, so a 2D image will be a two-dimensional signal. In fact, images can be considered as two-dimensional signals. If it is a signal, then it will have frequency also. Yes or no? Come on, tell me. Signal will have frequency, is it not? So if image is being considered as a signal, tell me what is the high frequency and a low frequency in an image? What is the high frequency and what is low frequency in the image? So whenever there is a transition from background to the foreground, what is my background? Yellow. What is my foreground? I am the person. I am the foreground. My background is yellow. Correct? So whenever there is a transition, so for example, that shirt, the edges, these edges, there is a transition. There is a huge transition from the pixel values. The moment there is a huge transition of the pixel values, those are high frequency regions. The background is a low frequency region. Okay, that's how the signals are interpreted in images. So in fact, you can have frequency domain filters also. We will not talk about that. In fact, that's a very interesting topic. Okay, you can do a fast Fourier transform of your images. See, signal processing, FFT of a signal, everyone has heard. If you're coming from a electronics background, mostly, you might have heard this. FFT of a signal, fast Fourier transform. So if image is a signal, you can also conduct fast Fourier transform of your images. Yes, and convert your images from spatial domain to time domain. And after converting your images from spatial domain to time domain, you can again apply time domain filters, frequency domain filters. So we'll not talk about any of those. Right now, we are talking about spatial domain filters. If you're really interested, you can just do a Google search. Frequency domain filters. And again, you will get high pass filter for images, low pass filter for images, band pass filters for images and everything. Okay, you can apply. So if you have a high pass filter, you will get edges. If you have a low pass filter, you will get the foreground. Okay, background. Okay. So you can have band pass filters and proper filters designed frequency domain in frequency domain, and again you can do sharpening operation, edge detection, and those things can be done by designing filters in the frequency domain. Right now we are talking about filters in the spatial domain, where you can see the numbers as an array of numbers. Okay. Too much technical. Coming back to the basics. Very back to the basics. We'll not discuss all that, as I said. Okay. Now. Okay. Now this is a very, very important question. Okay. Very important question here that I'm discussing. How do I decide the dimensions of the feature map. Do I get the dimensions of the feature map? Okay. Coming back to the code for the moment. Let's go to the code. Okay. So this is my image, original image, and this is the kernel or the filter. And I'm just visualizing that. Don't worry, there's nothing. I'm convolving this with this image, and this is the output that I get. So what function I'm using? Convolve 2D. Where is that function located? That function is located in the signal processing module of SciPy. I'm not going to use this function, however, for neural networks, but I'm just showing you the convolution operation can be done out of Keras and TensorFlow also. Okay. So I'm using a 2D convolution function. Why? Because my image is 2D. This is my filter. This is my filter. I'm going to convolve this filter with this image and see this is the output. Beautiful. Beautiful. Can you see the edges are enhanced? Right? Yeah. So this filter is 2D, Ashwin, not 3D. It's a 2D filter. It has just length and breadth. Okay. Just one dimension. Sorry, 2 dimensions. It's a 2D filter. Okay. It looks like an embossed image. Very good. But mostly the edges are enhanced. Can you see the vertical lines, horizontal lines, diagonal lines? So edges are enhanced. Very good. So this is your feature map. Exactly. This is my feature map. Okay, perfect. Okay, before I go to the pooling layers, I can just show you the code. Conv2D. What is this Conv2D? This is the actual convolution 2D class that I'm importing from Keras.layers. Okay. What is 32? 32 is the number of filters that I'm going to apply. This is the hyperparameter. Don't ask me why 32. You have to experiment. 32, 64, 128. You can apply as many filters you want. Fine. So this is 2D. For a 2D image, this is 32, the hyperparameter. Okay. So total number of filters. What is 3 cross 3 here? This is the dimensions of my filter. Dimensions of my filter. 3 cross 3. Simple. Input shape. Now, why is it input shape 28, 28, 1? Because we are working with that. Yeah, previous. So 784, we had got, you remember? 28, 28, 28 pixels height, 28 pixel width. And this one shows one plane. So the depth is 1. Okay. So we are converting the images in a way to 3D. Okay. But so you are feeding the images as it is. Okay. Without reshaping it. Earlier we were reshaping it to 1 cross 784. Now that is not needed. So the input shape is exactly 28 by 28 and one plane. Everything in one plane. Okay. What is padding? We'll see that. Okay. Don't worry. And activation, I think I am again using value. So see, this is how you use a convolutional layer. This is my convolutional layer. The output of this convolutional layer is a feature map. But the question is, if I just show you this number, how do I get this number, output shape? So what is this output shape? This is the output shape of the convolutional layer. How do I explain that it is 26 cross 26 cross 32? Is my question. Okay. What I'm asking is, I'm using 32 filters. I'm using 32 filters of 3 cross 3. Okay. Tell me, why is it 26 cross 26 cross 32 as the output of the convolutional layer? Input to the convolutional layer is, you have seen, the input to the convolutional layer is your image, 28 cross 1, because there is one plane. Okay. How do you calculate the dimensions of the feature map or the output? So that is what I'm going to tell you. So this is a simple formula. This is the simple formula. Okay. Output feature map. So W plus 2P minus F divided by S plus 1. That is the length. And again, length means the width of the feature map. And this is the height of the feature map. This is how you can calculate. What is W? W is the width of your original image, which is right now 28. 2 times P. By default, this P is 0. Okay, so that is gone. F is what? The size of your filter. That is 3. So 28 minus 3. 8 minus 3 is what? 25. Divided by S. By default, stride. S is stride. S is stride. What is stride? I'll tell you. But by default, it is 1. So 25 minus 0, by default, that is 0, I told you, right? Default padding is 0. So 28 plus 0 minus 3 is 25. 25 by 1 is again 25 plus 1 is now 26. Same calculation. The height also contains 28 pixels. This is again 0 to P minus F. Minus F is again 3. So 28 minus 3 is 25 divided by 1 is again 25 and plus 1 is 26. That is how you get. Please look at this. So if you are applying a filter, 32 filters of 3 cross 3, you are applying 32 filters of 3 cross 3 on an image which is 28, 28, 1. That was your image in the code, right? Your image in the code is 28, 28, 1. Your image in the code is 28, 28, 1. And you are applying 32 filters of 3 cross 3. The output dimension is 26, 26 cross 32. Why 32? The depth of the feature map is always equal to the number of filters. How many filters are we using? Come on. We are using 32 filters. So how many features are we going to get? 32 features. Simple. And how do you stack those features? One below the other. I'm stacking 32 features, one below the other. So the depth of the feature map will be 32. How many layers of features I will get? 32 layers of feature I am getting. Why 32 layers of features? Because 32 filters are being applied. Each filter is going to give me one feature map. Okay, that is one plane of features, one plane. What is the dimensions of that plane? 26 pixels by 28 pixels. How did I get that? By using this formula, which I demonstrated. Questions? This number became 26, 26, 32, and that is exactly what you are getting in the model summary also. 26, 26, 32. Why is this 26, 26, 32? Is that making sense? Oh, wow. We still have 57 participants. We started with 65 and we still have 57, even after extending it by almost half an hour. Right. So now listen to me carefully. If I am applying filters of 5 cross 5, what will happen? Can we calculate? Can we calculate? See, I did this calculation here. So if I'm going to use 5 cross 5, if I'm going to use 5 cross 5, so this will become, so here I'm doing the calculations. You can see. So this will become 28 plus 0 minus 5, which is 23. I1 is again 23 plus 1 is 24. In that case, you will get 24 cross 24. 24 cross 24 cross 64. Yeah. I think this is very simple. This is very simple. This is the formula which you can get anywhere easily. The question is, how do I calculate? See, you have to give the right questions to ChatGPT to get the right answers. So your question is, how do I calculate the actual dimensions of the feature map? Ask this to ChatGPT. It will return you this formula. It is as simple as that. I cannot explain you the calculations the way I'm explaining it, but it will definitely return you this formula. Okay. Now, the only two things which are remaining that we have to understand is, number one, what is the padding? And number two, what is the stride? Other than these two, okay, I'm taking sufficient time to explain convolutional layer because there is nothing else remaining. Because everything else is same. So if you're still not convinced, you can see everything else is same as dense. You have been knowing this, you have been using this. Only difference here is this line of code, which is, sorry, this is not needed. This one line of code and this another. So that's what I have been telling you. We just have added 2 lines of code. For convolution, one is for pooling. So the entire session is only to explain these 2 lines of code. Yes. Why we are doing and what is happening. This entire 2-hour session we are spending only to explain 2 lines of code. Everything else we have been doing. Come on, tell me. There's nothing else. You see, everything is simple. It's as simple as that. Okay. So can you explain the parameter value calculation? Yes, I'll come to that. I'll come to that later. But let us first understand the the feature map dimensions. Is there any questions on the dimensions of the feature map calculation? So the depth of the feature map will always be equal to the number of filters being applied. So if you're applying 64 filters, the depth will be 64. Is that clear? Let's see some of the pre-trained models available to us. XNet. Can you see here? I'm just highlighting something. This is AlexNet. Okay, this is a pre-trained model easily available. AlexNet uses how many filters? Come on. Uses 96 kernels. So the depth is 96. Then in the next layer, it applied 256 kernels. So here the depth is 256. Okay. This is 227, 227. What is the dimensions of the feature map? Come on. Okay. This is using 11 cross 11. So 227 plus 2 times 0. So that is 0. I'm assuming padding is 0 minus the shape of the filter. So what is the shape of the filter? 11 divided by stride, which is 1 plus 1. Come on, tell me what is the value. 227 minus 11 by 1. Tell me the value. 227. Why is this 0? Because of padding. Why is this 11? Because of 11 cross 11. No, that is the filter dimension we are applying. Okay, one thing, sorry, I missed is the stride. The stride is not 1. The stride is not 1. They are using a stride of 4. So this should be divided by 4. Now tell me what is the value. The stride is 4. What is stride? I'll tell you, but let's look at the formula first. 55, you see, 55 cross 55. Yes? So this is how you get 55 cross 55. And why is it 96? Because we are applying 96 kernels. And that's how the entire calculation goes. So in the next one, they are applying another stride of 2 and so on. So let's not get involved in that. But I think this is clear to everyone, correct? How these numbers are populated. Very good, very good. Congratulations. You are at an intermediate level of CNN as of now. Okay. The next 5 minutes, you will become advanced level. Okay, when you understand the concept of padding and stride. Okay. Now what happens here is, can you see, not this image. Okay, this image. If you see this image, something interesting I'll show you. See, your actual image starts from here. Your actual image starts from here. This is your actual image. This is your actual image. But what did I do? If you notice, I have added one layer of zeros here, one layer of zeros here, and the same I would be doing. So I would be enclosing a layer of zeros, and this is called as padding. This additional layer of zeros is called as padding. This additional layer of zeros, can you see? This additional layer of zeros that has been manually added to the image. That has been manually added to the image. Why? Answer is very simple. Answer is very simple. Because I want my output feature map to have the same shape as the input image. Once again, I repeat this statement. Listen to me very carefully. Why did I add that layer of zeros? That is called as padding. How many layers of zeros of padding I want to add? There is a simple calculation, I'll tell you. But why did I add that padding? So as to ensure that the shape of the output feature map is exactly same as that of the input features. See, are you currently? See, this is 28, 28, 1. But this is not 28, 28, 32. This is smaller. Your feature map is smaller. Please listen to me carefully. Your feature map is smaller. I want my feature map to be 28, 28, 32. And when can that be possible? That is possible only if you add those 2 additional zeros layer. Here, 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 and here. 2 additional layers of zeros everywhere. Why 2? Because you have to make sure that 28 plus 2 is 26 plus 2 is 28. Okay, something like that. So here the objective is very clear. Okay. By default, okay. Yeah. So I think I have mentioned here. Yeah, padding same ensures that the shape of the output feature map, padding same ensures that the maybe I can here padding is valid. So model dot summary. If I say padding is equal to same, then what will happen is automatically strips of zeros would be added so that the shape of the output feature map is exactly same as that of your input image. That is exactly what I was going to tell you. Okay. I do not want to lose any information present at the edge of the images. That is the motivation. Okay. If you use padding as valid, which is default, this is the default, you will lose information present at the edge of the images, unfortunately. Whereas if you use padding as same, then automatically those zeros get added such that the output feature map has the same shape as the input image, and that edge information of the images is retained. That is the beauty. Edge information present in the image is retained. Okay. So if original image was 28, 1, and you applied 32 filters of 3x3, and you use padding as valid, then the output feature map would be 26, 26, 32. Whereas with the same, you would get 28, 28, 32. That is exactly what I'm trying to tell you. This is the output. Okay. And with valid, let me show you that once again. So I'll change this to valid. Can you see? I'm changing that padding to valid. Beautiful. So this became 26, 26, 32. I think now it is very, very clear, correct? I think that is very, very clear. Padding equal to same is generally to be used when you have some valuable piece of information along the edges of the original image. Otherwise, you can leave it to the default. Default is valid, not same. When using valid, the information at the edges will be lost. You have to keep this in mind. So if you have a very small image and that too a lot of information present at the edges, you have to be careful. If you have a huge image, then there will be hardly any information, especially this kind of image where the subject is present in between and all the edges of my camera. Can you see? It's just the background. So 3 sides, it's only the background. And only at one part of my image right now is the person speaking. And that too, this part is your white strip. Can you see this part? At the edge is also a white strip, hardly any information. Because to identify face is present at the center of the image. So if your objective is to identify whether this face belongs to Prashant or not, you can very easily use padding it to valid, because Prashant's information is not present at the image boundary. It is present at the center of the image. Is that clear, everyone? Yes or no? So you don't need the edge information to identify that this guy is Prashant, because Prashant's features are present at the center of the image. Okay, so most of the people will go with the default. That is what it is. Okay. So what is stride? So while jumping, so what did I say? So this is how you are applying, right? This is how you are applying. Now, if you apply here and then you apply here and then you apply here, so what is happening? You are jumping. So you applied here and then you applied from here and then you applied here and then you applied here. That is like jumping. Jumping means you are skipping some of the columns. Please understand. Okay, so you started from the first column and then you skipped the second column and you started from here. Then you skipped the fourth column again, you started from here. Okay, so if you are skipping, you are not continuously moving. Please understand, you are not continuously moving. You are skipping some of the columns. That is called a stride. So by default, stride is 1, which means you are not skipping any of the columns. But if you say stride is 2, then every alternate column would be skipped. Stride of 3, every 2 columns would be skipped. Not only horizontally, but also vertically. Okay. So if this was your, look at this finger. Okay. And then instead of starting exactly from here, if I'm starting somewhere, we should ideally be starting somewhere from here. Sorry, here. But if I'm starting from somewhere below or further below, that means I am, skipping some of the rows also while doing the stride. Okay. So if you are skipping some of the rows or columns, then obviously the shape of the feature map will be further smaller. So if you skip every alternate row and column, then the stride is 2. And so the size of the feature map will be half, literally half, because you skipped every single alternate row and column. No. So the shape of the feature map would be half. If you skip 2, then it will be 1/3 and so on, right? Exactly. So where do you provide the stride? If you go to the documentation, just looking at the documentation of this layer, convolutional layer. So you can provide the stride also. Okay, not padding is either valid or same, and stride, correct. And stride. Okay, so let me start concluding now. I have taken enough time. Okay, I know everyone is hungry. Even I have been getting calls from home now. Where is this guy? Okay. So give me another 5-7 minutes. Okay, because code is nothing great. Okay, so what we have got is the feature maps, and what are we going to do with the feature map? That is one thing we have to see here. So we have got the feature maps, which is this now. The next operation is we are going to run. We are going to run activation on my feature map. So typically a ReLU activation. Okay. So once again, I repeat, the output of the convolution operation is the feature map. You are going to run your activation function on the feature map. So what you have got is a rectified feature map. I'm using the word rectified feature map because I'm using ReLU as the rectified linear unit. That is your ReLU. Rectified linear unit is the full form. So I'm using rectified linear unit as the activation function. So all I have got is the rectified feature map, and that rectified feature map goes to the next layer, which is my pooling layer. This goes to the pooling layer. Okay. So this is the input image. Then output is a feature map. The feature map is activated or rectified, and then this rectified feature map goes to the pooling layer. So how many operations? So first is your convolution operation, and then you get the feature map. Second is your activation. So 2 steps. Okay. Convolution, rectification, 2 things. And so this goes to the pooling layer. What does the pooling layer do? Listen to me carefully. You have extracted so many features. But then, are all the features important? I want my model to focus on the important features. And that is what the next layer does. It pools the important features. It concentrates the important features. So that concentration can be done by multiple operations are there. We'll not get into more details. Okay. But that is exactly done by the pooling layer. Okay. So you have the image, you have the convolutional layer that gives many feature maps. Feature map will be rectified. This is exactly what I mentioned, followed by normalization if you want to do. And then the output goes to the pooling layer, which is going to concentrate the feature maps. So they pool out the important information from the pixels. This is essentially feature selection, if you have not understood. So what is convolutional operation? That is feature extraction. What is pooling? Feature selection. It is as simple as that. Come on, tell me if this is confusing. Convolution layer is extracting the features. Pooling layer is selecting the features. It is so simple. It is so simple. Okay. So we'll not get into all the numbers and all that. Okay. But this is that simple. Let's go back to the code. So I extracted features from here and then pooled the important features from here. And then you still have to flatten it so that, see, I've got the features. I've got the concentrated features, selected features, but there has to be someone to learn the features. There has to be someone to learn the pattern in the features. Who is going to learn the pattern in the features, my dear? This fully connected layer will learn. This fully connected layer will learn the pattern in the features. Simply feature extraction, feature selection is not enough. Someone has to learn the features also, right? So this hidden layer, this dense layer that I have, okay, is going to do the learning. And finally, you have the output layer. It is as simple as that. So you can have more number of dense layers also, as it is mentioned in the, as it is mentioned here, okay. You have seen, right? So you can do back-to-back two convolutions and pooling. That is also very much valid. This is also very much valid architecture. And then you can repeat that. So here back-to-back two convolutions, they did back-to-back three convolutions. So features, then features, then features. So 3 layers of feature extraction followed by concentration. Then again repeat. So can you see? Followed by, there are 3 dense layers. Why are these 3 dense layers still needed? Papa, there has to be a reason, right? Why are these 3 dense layers still needed? They are learning the pattern in the extracted features. But the problem is you cannot connect the, see, till here, all your image is always 2D or 3D. Please understand. The image is always 2D. So here the outputs are all 2D or 3D. But the input to the dense is always 1D. So there has to be a mechanism to convert your 2D or 3D or even 4D into 1D. And that mechanism is your flattening operation. So you are going to flatten your feature maps, which are 2D, 3D, or 4D. See, the output would be a concentrated feature map of this last pooling layer, right? So that has to be flattened. If you do not flatten, you cannot connect it to the dense layers because dense layers are one-dimensional. Okay, that is the problem. So you still have to flatten it. So that's what I did in the code also. I flattened it. And then I connected with 1 dense layer. You can make 2 dense layers, 3 dense layers, doesn't matter. And then simple model building is done. One additional thing, if you want, you can do is like batch normalization. If you want, okay. But we can discuss that sometimes later, okay. So you are doing the pooling. By default, the pool size is 2 by 2. Now, what is this 2 by 2? It is going to reduce the feature set by half, literally by half. So that was 26, 26, 32. That will become 13, 13, 32. You can see. Beautiful. Okay. Why is that 13, 13, 2? Answer is very simple. I'll take 1 minute to explain. So imagine you are dividing your feature map. You are dividing your feature map into boxes of 2 by 2. So these are the boxes of 2 by 2, 2 by 2, 2 by 2, 2 by 2. So your max pooling is taking the maximum number out of these blocks. So maximum number here is this, maximum number is this, maximum number is this, maximum number is this. I'm just pulling out the maximum numbers from these blocks. So you are dividing the entire feature map in these blocks of 2 by 2 shape. Yes. And from each block, you are just pulling out rather, the max value. Or you can use the average pooling. So these are the 2 most common things. Average pooling means you take the average of these 4 numbers. So I think that is present in the next slide. See, easily your 4 cross 4 has become 2 cross 2. That is the thing. Okay. Yeah. So you can have average pooling or max pooling. So mostly people go for max pooling. So where in the max pooling, you are pulling out the maximum number. So the max value is this, max value is this, max value is this, and here the max value is this. or you can take the average of these four numbers, which will be, sorry, average of these four numbers, which would be 8, average of these four numbers, which is 79, and average of these four numbers, which is, that is called as average pooling. In any case, after pooling, you have to flatten so that you can connect it to the dense layer. So what is the final architecture then? Yeah. So this is the final architecture. Your image, you can conduct k times convolution followed by pooling. And this convolution pooling can be repeated n number of times. So what happened in the VGG16? Value of m was 4. Can you see? In the case of VGG16, 1, 2, 3, 4, 5. Sorry. The value of m is 5. I'm repeating this entire 5 times. And convolution, how many times I'm repeating? I'm repeating 2, 2, 3, 3, and 3. Right? So I can repeat this convolution operation 2 to 3 times, followed by pooling. And then this convolution pooling block can be repeated 3, 4 times or even 5 times. And then either you use a flattening operation or you use a global average pooling. That also does the job similar to flattening. And then you can connect n number of fully connected layers. What is the value of n here? The value of n here is 3. In my code, it is 1. Followed by output. I have given 2 star marks here. So one is you can do a batch normalization between convolution and pooling. That is optional. And you can do dropouts in the fully connected. So dropouts and batch normalization, these are techniques for preventing your convolutional neural network from overfitting. Okay, so they act as regularization in a way. Okay, so we'll not discuss more details about that. Maybe sometimes in the next session, I might discuss about normalization and dropout. But this is optional. As I said, I do not have it in the code here. So that is why I'm saying it is purely optional. Okay. So if you want, I can show you how will the code for this is batch normalization I did between convolution and pooling. And if you want to use dropout, that has to be used between 2 dense layers. So you need to have at least 2 more dense layers. Okay. And between them, you can have a dropout. Everything else is same. So same training, same, everything. Okay. What I did was further to extract the layer, and I can show you the weights also. See, these are the weights. These are the actual kernels. Okay. I just use a simple extraction. And after extracting, I'm printing the filter values. That's it. I'm just printing the filter values. Even that can be done. Okay. So I'll end it here. I'll share this notebook. Okay. So I have tried to give you a very thorough. In fact, I have tried my best to give you the very thorough overview of convolution and pooling. Why is it needed? How does it work? Okay. And you see, in terms of code, it is only 2 lines, but we took more than 2 hours to explain those 2 lines. Right? Because we had to start from bare basics, neural networks to basics of images. How does the computer interpret? And then unless and until you work it this way, you will not realize the power of neural networks. I mean, convolutional neural networks at least. Okay, so thank you guys. Thank you so much. Let me see if there is any unanswered question as of now.
Yeah, like before we proceed to answer your questions, I would like to request the attendees to fill the poll about feedback as it helps us to conduct more such sessions.
GitHub link. Yes. Don't worry. I'll give you the GitHub link for the previous one. So go to this GitHub data, copy link address. Let me paste it. So I think all my data are present here. So previous 4 sessions on sentiment analysis, you can get the codes. And this was the repo for the previous session on neural networks. I'll be adding now. I haven't yet done, but I'll be doing it tomorrow. It is already late. So in 1 or 2 days, keep watching this. You'll get another folder called as CNN. Okay. And that will be added there. Okay. So let me just pause my instance. Any questions? Let me check. Share the PPT and everything will be shared. Don't worry. Is there a standard rule to select the kernel size? Yes. Normally, we go for smaller kernels than bigger kernels. So the smallest kernel people try is 3 by 3. So as of now, the state-of-the-art convolutional neural networks do not use 5 cross 5, 7 cross 7, or 11 cross 11. That was a grave mistake which people did earlier. Now, everyone is going for 3 cross 3 because of the results that we have got. Now, that's like a experimentation knowledge we have got. Okay. So don't waste time in experimenting those kernels. 3 cross 3 is the best and works mostly. Can we apply ReLU to sentiment? Yes. ReLU is applied everywhere. Don't worry. Yeah. So that is also answered. Anything on the chat which I missed? Thank you, Kumar. Okay, so I'm leaving now. Thank you.